All right, I think we are ready to get started. I put this warm-up up here just because it's the warm-up that was supposed to be for today. Some function, least value of x for which f changes concavity. I want to find the second derivative of this, right? And then let it equal 0. Those are my critical points. And then I'm plotting or I'm plugging in values around the critical points to determine where it does change concavity. And then I'm looking for the value of x that is smallest. Right. If you have the notes printed out, the answer I believe is B, 0.93. Okay. But we have a lot to talk about today. So we're not going to get into this too much. Today's lesson is about Taylor and Maclaurin polynomials. Today's kind of a big deal because this is your first introduction to an aspect of calculus that is really the analysis of functions. Okay. The idea of a Taylor or Maclaurin polynomial is to be able to represent some function. For instance, the cosine of x, to be able to represent that function as a series of polynomials. Well, as a series, that series being a polynomial. So the idea is if f is differentiable n times, then the Taylor polynomial of degree n, about x of 0 is, all right, and then we have x of 0 plus f prime of x sub 0 over 1 factorial, okay, x minus x sub 0 plus f double prime of x sub 0 over 2 factorial, x minus x sub 0 squared, righto, so on and so forth, all the way up to f of x to the nth derivative over n factorial times x minus x sub 0 to the nth power, which can be represented as the nth derivative of x sub 0 over n factorial times x minus x sub 0. Yes. To the n. Okay, so here we have a formula for finding, this is noteworthy, okay? This is our formula for a Taylor polynomial. Okay. Remember, a polynomial is a function whose terms are made up of like linear, quadratic, cubic functions up to some degree n. And what this does for me is allows me to estimate a function around a point using its derivative. Okay, and we can represent it as a series. Let's see. The Maclaurin series is a special type of polynomial or Taylor polynomial where the point that I'm centering about, right? Notice that this is the Taylor polynomial of degree n about some point. Okay. If I wanted that point to be 0, I get a special polynomial called a Maclaurin polynomial. So in the case of cosine of x, it could be represented as the series of functions that might look something like this. Right, there's my linear function, and then I would have a squared or quartic function, and then some cubic function, so on and so forth. So the sum of these functions estimates the function. Let's see. If you print off the notes, it's a lot of stuff for me to write up on the board. If you print off the notes, the formulas are there for Taylor and Maclaurin polynomials of degree n. The one thing, this is going to come easier with practice. It's just a matter of using the formulas. I need light. All right, let's see. All right, let's jump into doing an example. We're gonna This is the Maclaurin polynomial. Instead of writing Maclaurin polynomial out every time, I'm just going to abbreviate it as MPoly. Right? Find the Maclaurin polynomial for e to the 4x of order n equals 0, 1, 2, 3, 4, and n. Okay. All right. There's our formula for the Taylor polynomial. And we said the Maclaurin polynomial is a special kind of Taylor polynomial where x of 0 is 0. So the formula for an n or a Maclaurin polynomial that's not right. That was right. Okay. All right. so the formula for a Maclaurin polynomial is just like the formula for the Taylor polynomial, except x of 0 equals 0. So I plugged in 0 here. X minus 0 is just x. All right. Okay, so you can tell we're going to be needing to find numerous amounts of derivatives. So let's do those first. All right, so this would be degree 0, 1, 2, 3. We also want to look at degree 4. See, 4 times 64 is 256. I should know that. All right. So for the Maclaurin polynomial, for these various derivatives, I want to be plugging in 0. Well, e to the 0 is always 1. Okay. So f of 0 is 1. F prime of 0 is 4. F double prime of 0 is 16. F triple prime of 0 is 64. And f to the fourth prime, or f, the fourth derivative of f of 0 is 256. Okay, so we'll write the polynomials out this way, and then we'll write the general polynomial, right, to the nth power out here. All right, so I want f of 0, which is 1, over 0 factorial times x to the 0 power, which is 1. So the Taylor polynomial, excuse me, the Maclaurin polynomial for the function e to the 4x of degree 1, or excuse me, of order 1, is just 1. Okay, if we go out to the second term, we get now 4 over 1 factorial times x to the first power, which is 1 plus 4x. This, order 2. That's going to be 8x squared. All right. Of order 3, we have all of this stuff plus the next term, which is 64 over 3 factorial x cubed. So it's just this with that tacked onto the end. And then order 4, we add on the next term, 256 over 4 factorial x to the 4th. All right. So it might help to keep this as 16 over 2 factorial, because then it becomes easier to see of order n. So I guess we have space to put it over here. Right. We can see that. Okay. So of order n, it's going to be the sum as n goes from 0 to n. Excuse me, to infinity, because we want to go all the way. Of 4 to the n over n factorial times x to the n. Okay. So again, conceptually, what this represents is a series, right? It's a list of numbers that are being added together. In this case, it's a list of functions that are being added together. There's an infinite number of these functions, and if I add this infinite number of functions up, I estimate that function. Well, actually, I get that function if I carry it out to infinity. I estimate the function around 0 for points really close to 0. All right. So let me stop and see if there's any questions. You should be able to use the question application. If not, I'll check my email and see if there's any questions there. Yeah, let's see. Okay. All right. So I'm going to keep this up for a second because I want to talk about, as we go through this, I want to talk about some special polynomials. Okay. One of the special Maclaurin polynomials that we know is e to the x. Okay. The Maclaurin polynomial for e to the x is x to the n, yeah. Okay, which is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus dot, 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 x to the n over n factorial. Okay. So if you're ever asked for the Maclaurin polynomial for e to the x, that's what it is. It's always that. You never have to derive it again if you memorize this. But if you know this, it makes coming up with the Maclaurin polynomial for e to the 4x much easier, right? Because all I'm going to do, if this is e to the x, e to the 4x is this same thing, but everywhere I see an x, I'm going to plug in a 4x. That's my 16 And that is just another way of writing that. Right? So knowing some of these special Maclaurin polynomials, which are listed in your notes, but I believe they're also listed on page 657, 75. Okay. So go check those out. It's going to be really important that we have at least the e to the x, the sine x, the cosine x, the tan x, and 1 over 1 minus x memorized. That's going to make your life much easier. So, all right, let's do another example here. So let's do a Taylor polynomial example, unless we have some questions. Let's see anything that's coming in. You guys remember, just email me if you have a question, or try to use that question tool if you do have questions. I'm going to leave this up so that we have the formulas with us at all times. All right. Okay, I'm going to sort of abbreviate the question here. I want the Taylor polynomial for the function e to the x at x equals 2. And I want it of orders 0, 1, 2, 3, and 4. And then we'll find the general. Okay. So now this is going to be slightly different than that special Maclaurin polynomial I just showed you. Remember, the Maclaurin polynomial is a Taylor polynomial centered at 0. Here we want to center this at 2. Okay. So that means my estimation of my function is going to be most accurate at x equals 2. In the Maclaurin polynomials, your series representation is most accurate at 0. Okay. So we're going to use this formula. It's the same formula. We're just plugging in a different value. Okay. So I want the same derivatives here. Okay, so remember this can be thought of as the function with derivative of order 0, right, which is just the function itself, right? That's my order n equals 0, okay, which is just the function. All right, e to the x, this is nice and easy. That's why e to the x is the most beautiful function on earth. All right, now we're going to be plugging in 2 instead of in the previous example where I plugged in 0, right? Remember, Maclaurin polynomials, x sub 0 is 0. In this case, I'm centering around 2, okay? Okay, so we have e to the 2, excuse me, e to the 2, e to the 2, e to the 2, e to the 2, e to the 2. All right. So now to put the pieces together, I'm gonna write the entire series out here instead of writing each individual series, because hopefully you've picked up that the Taylor polynomial of degree 2 contains the Taylor polynomial of degree 1 and of degree 0, right? So my first term is going to be e to the 2 over 0 factorial. Okay. Of degree 1 will be e to the 2 over 1 factorial times x minus 2. Of degree 3, or of order 3, it's going to be e to the 2 over 2 factorial x minus 2 squared. All right. So I can represent this as the series, and I'll get out of the way in a second. E to the 2 x minus 2 to the n over n factorial. Okay. So the function e to the x, right, which we know looks like this, at the value x equals 2, right, I can start adding up some functions, which creates a polynomial that estimates the shape of that graph. Okay. Let me get into that a little bit more while we're here. So if I were to just look at n equals 0, then I just have the value e to the 2, which should be right here. If this is the function e to the x, when you plug in 2, you get e to the 2. All right, so it's this line. So obviously at 2, we're extremely accurate. Okay, if I were to try to use that to estimate e to the 3, well, it's just going to give me back e to the 2, right? It's not very accurate. So I go out a little bit more, and now I have a linear function, right? Okay, this is my n equals 1. Okay. That has a slope of e to the 2 it should look like that. So now I have sort of a linear approximation that we looked at in the past. Here's n equals 2, and now I have a quadratic. Okay. And this quadratic function opens up okay. And you can see how that curve of the quadratic gets much closer to estimating the curve of the exponential function. Okay. And then we can keep going and keep going. And each time we add on a new term, the curve that's graphed estimates the shape of the curve much, much better and at a wider range around 2. Okay. So that's sort of conceptually the purpose of what we're doing is we're looking for another way to get an estimation or an approximation for values of a function, right? Without just being limited to the linearization that we talked about in earlier chapters. Okay. It's also going to make it much easier to play with certain functions that don't necessarily play well with each other. All right. No questions yet, but we keep. Ryan Gates. What is the point of finding the Taylor polynomials? What does it tell us? Also, I went to the help bar and it said that the host has to enable. I thought I did. Let me double check on that. I thought I had enabled it. Dang it. All right. I guess I'm sorry. I thought I had enabled it. All right, well then just, I guess, send me an email if you have a question. I'm sorry, I thought I had enabled it. All right, so Ryan, your question I think I answered. Why are we finding these polynomials? To estimate functions. All right. Taylor polynomials, Maclaurin polynomials are used in computing because polynomials are really easy to represent in code, but non-transcendental functions or transcendental functions like e to the x and sine x are difficult to cat problems are difficult to represent in computing. So Taylor polynomials gives us a way to do that. It gives us a way to represent these very interesting functions that sort of curve and are predictable but don't follow the rules of polynomials. Right? In general, in mathematics, polynomials are really easy to play with, right? They're easy to find zeros for. They're easy to solve, but some other kinds of functions are more difficult to solve, like e to the x, sine, cosine, tangent. Those are difficult to solve sometimes. So, okay, find the Maclaurin polynomial for sine x. All right, so if you haven't looked in your textbook already to see that the Maclaurin polynomial for sine x is one of our standard, our special Maclaurin series, we're going to find out what it is, okay? So we want the Maclaurin polynomial for sine x, okay? So we're going to do a few terms, and then we're going to try to generalize it and see if we can't come up with it on our own. All right. So I want the function, its first derivative, its second derivative, its third derivative, and we'll go to the fourth. I did that one wrong. And now we're sort of back to where we came, or back to where we started, which is okay. We could keep going. We could keep going and do this all the way up to n, but we're just going to stop here. So remember, Maclaurin polynomial, I'm centered around 0. So I'm using that bottom formula over there. So I need to find f of 0, f prime of 0, all the way down. Okay, so sine, right? Sine of 0 is 0. Cosine of 0 is 1. Negative sine of 0 is 0. Negative cosine of 0 is negative 1. Sine of 0 is 0. Okay. So now let's plug it into my formula. I have 0 over 0 factorial times x to the 0. That was this. The next term. Are you kidding? Cosine of 0 we said was 1 over 1 factorial x to the first. Okay. Then we have negative 0, which doesn't really mean anything, over 2 factorial times x squared. And then we're going to have a minus 1 over 3 factorial x cubed. And then we're going to have another 0 term. Okay. So notice this cancels out, this cancels out, this cancels out. All of the even terms are going to cancel out, including 0, right? 0 is not even, neither even nor odd. Or is it even? Because it can be written as 2 times a number, but it's itself. I don't know. That's a question for another time. So in general, I have, let's see, x minus x cubed over 3 factorial. Okay. And then we'll have plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. And you can continue this out to see that on your own. So sine of x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. So the function sine x, its special Maclaurin polynomial is this. So if I were to ever ask you for the Maclaurin polynomial of sine of 3x, all you would have to do is plug in a 3x everywhere you see x, and you wouldn't have to do this anymore. Right? Let's see, let's do it this way. Zero to infinity of, what do we want to do here? It's I guess we could just say it's x to the n over n factorial, and then yeah. All right. All right. Let me check for questions. Okay. All right. Represent f of x equals sine x. Okay, so quick review here. We've looked at how to generate a Taylor polynomial. We've looked at how to generate a Maclaurin polynomial. There are special Maclaurin polynomials that you should know. 675. Okay, are those special Maclaurin polynomials? Again, Maclaurin polynomials is nothing different than a Taylor polynomial, except that you're centered around 0. Right? It's a special kind of Taylor polynomial. All right. I'm going to skip that last polynomial generating example and go and look at the Lagrange error bound theorem. So, from what I've heard, there's always a problem on the AP test about Lagrange error bound. If you remember when we were talking about, was it the Unit 7 test, where you had to determine the error in some Riemann sum, right? This is sort of similar, okay? Let me go back up here so I can see what the theorem is and write it out. So, this is called either Taylor's inequality or Lagrange. Did I spell that right? I did. Lagrange error bound. Okay. If this is the n+1 derivative of some function is less than or equal to some value m for all x in the interval, all x in the interval, whatever that interval happens to be, then the remainder R sub n of x of the Taylor series satisfies less than or equal to n over n plus 1 factorial times x minus x sub 0. And those are absolute value signs to the n plus 1 for all x in the interval. So what this is saying is if I can find some value m that is greater than or equal to all values of the next derivative higher than the error I am calculating for, that error is less than or equal to the value of m over the n plus 1 factorial, blah, blah, blah. All right, so very similar to the concept we talked about in Unit 7. All right, so let's look at an example. So use Lagrange error bound to find an interval containing x equals 0 over which the function f of x will be approximated. Okay. So I need this space, so make sure you have this down because I'm going to erase it. So use Lagrange error bound (leb) to find interval such that f of x can be can't see that. Okay. So we want to use the Lagrange error bound to find an interval containing x such that some function, the function we're going to use is sine x, so what we want to do is determine how many terms I need in my series to be able to say that for all values of x within this interval, I am within an error of the actual function that is approximated to the third decimal place. Okay. So remember, my Taylor polynomial is for sine of x. Oh, we haven't talked about sine of x. That's okay. The Taylor polynomial for sine of x is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, so on and so forth. Okay. All right. Okay, so let's see. Oh, why did I say that? Oh, it's cosine. We want to use cosine of x, and that makes me feel like I did this one wrong. Oh no, yeah, we did sine of x. Cosine of x is the one we haven't talked about. Okay. And this is the Taylor polynomial for cosine of x. Sorry for the confusion. We're going to use cosine of x. It's the one that we haven't talked about. We talked about sine of x. This is the Taylor polynomial, or the Maclaurin polynomial that we're going to use. All right. So use Lagrange error bound to find an interval containing x of 0 such that f of x can be approximated using this. All right. So the derivative of cosine is sine, the derivative of sine is cosine, back and forth, back and forth. So the maximum value that this could be is 1, right? So we'll choose my m to equal 1, right? So if I can find some value, m, that is greater than or equal to the n plus 1 derivative, well, the derivative for this is always going to only have a value that is at greatest 1. So that makes finding m very easy. Since we're here at n equals 4. I'm going to choose choose n to equal 5. Okay, so that's the next term. All right. Okay. All right. So if I want third decimal place, that's right. So third decimal place. I'm just sort of getting things set up so I can plug it into my formula based on the question that was asked. It means I want my error to be somewhere like this, right? Because if it was, right. Okay, so third to the third decimal place. So we have the remainder out to the next term, right? It's going to be less than or equal to m over n plus 1. So n I chose to be 5, so we'll have 6 factorial times x minus x sub 0, which in this case is 0, to the n plus 1 power. Right. And I want this to be that. All right. So 1 over 6 factorial times x to the 6th. So now we just need to solve for x here. Multiply by 6 factorial. Oh, these numbers are nutty. 0.36. Okay, and then take the 6th root, and I get something like 0.84343. Okay. So the interval I'll choose is negative 0.84343 to 0.84343. Excuse me. No, kitty. No, kitty, it's my time. All right, so I'm estimating this function using this Maclaurin polynomial, okay? I chose n to be 5 because this was the 1, 2, 3, 4, 5th term, right? So n was 5, and so I want my my remainder after the 5th term, right? I'm using n plus 1 here, and n plus 1 here, and I want this to be accurate to the third decimal place. So 0.0005 will be 5. Yes. All right. So, yeah. I see a question. Your Lagrange air-bound example is cosine. Oh, okay. Sorry, I got to that late. Okay, I changed it. All right. That's really all the notes there are. I think it's nice. I always like to look at some sort of interesting things that involve Taylor and Maclaurin series. So let's see. Okay, so here we have two special Maclaurin series, cosine and sine x. Now let's just play around and what would happen if I added these two things together? Yes. I stuck an I in there. That's the imaginary constant, square root of -1. Well, I'm going to take every term of this and add it to every term of this. This is going to be multiplied through by I. So I have a, let's see, 1 plus ix minus x squared over plus ix cubed plus x to the 4th over 4 factorial minus x to the 5th over 4 factorial. That's got an I. Now this sort of looks like e to the x. The problem is there's a bunch of i's in there. Well, if we think back to how we generate my Maclaurin polynomial, this would be the Maclaurin polynomial of order 2 for e to something. Right. So let's see. Would have the first derivative. Let's see. F of x is e to the something x. F prime of x would be something times e x, right? And then let's see, e double prime of x would be that times that, e to the question mark x, right? All right, so let's see. This turns out to be this, e to the ix, right? So as I take the derivative of e to the ix, I end up multiplying by I, right? And when I hit an odd term, when I hit an odd term here, like the first derivative, right? I just have an I. When I hit an even term, I end up with an I squared. And so that gives me no I there, but a negative 1, right? And then, so this must be Ix. I squared. The third derivative would be I cubed, which we know is positive I. No. Negative I. What is it? Should that be negative and that be positive? Yeah, that's good. Oh, I got my signs mixed up. Okay, now it should work out. Okay, so that's just something that I think is cool. Another reason for doing Maclaurin and Taylor polynomials is you can now add functions. You're just adding polynomials, and the resultant is some other crazy function. Just allows us to do a lot more interesting sorts of things with functions that are typically hard to play with. Okay, now I did see that there was a question about the previous problem. Why did I choose m to be 1? Now, this was going to be the last thing I showed, and then that would have been it for class. I'm going to answer this question, so if you have any other questions about anything from today, make sure you send me an email, because after I answer this last question, I'm probably going to call it for the day. The theorem for Lagrange error bound says that if says this, okay? So that means I'm taking the next derivative of the function. My function was this, okay? And I went up to you can sort of see the pattern here. The next derivative is going to be either sine or cosine. And so the absolute value of sine or cosine is never going to be more than 1. So 1 is a number I can choose that is greater than any value of sine or cosine on any interval, right? So I hope that answers the question. Right, we chose n was, we said n was 5. So I'm looking at let's see, the sixth derivative of x to be less than or equal to m, the sixth derivative of x would be negative cosine. So this is always going to be either 1 or -1, and the absolute value is always going to be, right? So cosine is always between -1 and 1, right? So if I'm looking at the absolute value, it's got to be less than 1 for any value of x. Okay. I hope that answered that question. Let me see if there was anything else. All right, if that's everything, I'm going to go ahead and log off. You should be able to click the link in the Blackboard announcement that says YouTube link and be able to watch the video at your leisure. But I'll send out I'll put another announcement about that in Blackboard. So if anybody did miss today's lesson, they'll be able to view it. All right. Have a good snow day.